Да, Саша, ты скоро присоединишься? Я смотрю, просто видно, не обратил внимания. Там было только что уже 10. Было только что 7 человек, пока я ходил за телефоном, стало 10. Все, хорошо. Okay, so I think we can begin now. It's actually no. Okay, what's wrong? It seems I have problems. Just a moment. I cannot draw for some reason. Just a moment. I need to. Something's wrong with my tablet. I try to solve this problem. Just a moment. I might need to reload my laptop before I can. What's wrong with it? Okay. Oh, now I can draw. I'm sorry. I'm afraid that the network is very poor here, and I'm not sure if I can draw properly. I'll try to draw, but so. Okay. Yeah, I hope it will improve. Okay. So it's going to be a pretty simple talk, I believe. The subject of this talk is actually pretty well reserved to the papers we recently put into the archive. One is joint paper with my joint paper with Yasushi Ikeda, my PhD student, and the other one is our joint paper with Yasushi and with Alexander Molev from Sydney. So as far as the second paper is concerned, I'll probably only touch the subject covered in it, and as far as the first paper is concerned, I'll give more details about it of the things which we discussed there. So let me begin with something very simple. Suppose we have a manifold M with Poisson structure pi. Oh, sorry, something's wrong with the gain. Yeah, now it's better. The Poisson structure pi in it. It's wrong. For some reason I cannot draw. I don't know why. I hope it will improve with time. As you know, pi is any section of the exterior square of the tangent bundle of our manifold. And it verifies the standard equation that is Houghton-Bracken with itself vanishes identically. So if this is the case, then we can define the Poisson bracket on the algebra of functions on M by sending every pair of functions f and g of smooth functions on M to the value of the bivector pi on the pair of differentials df and dg. In this case, if this is the case, then this bracket verifies the skew symmetricity automatically, right? It verifies Leibniz rule automatically again, very simply, just because if you take differential of a product of two functions, this differential verifies Leibniz rule. And which is the most non-trivial part of this? It is that this bracket verifies the Jacobi identity, which is equivalent, in fact, to the equation that this Houghton bracket of p pi with itself vanishes identically. The Poisson structures are pretty widespread. They are much more widespread than, say, symplectic structures, which can be formulated as Poisson structure with non-degenerate pi. For instance, in every manifold, you can just define pi to be equal identically to 0, and then everything will be true. You'll have it. Still, when you have a Poisson structure, you have some additional constructions like, I don't know, Hamiltonian vector fields, Hamiltonian systems, in general Hamiltonian mechanics. And the idea of that actual mechanics should rather belong to symplectic structure rather than to Hamiltonian can be expressed by saying that we choose the central functions that is to say, Casimir functions. Such functions that the Poisson bracket with anything vanishes identically. This is also called sometimes Poisson center of the Poisson algebra. And restrict our attention from generic position in M to certain level sets of Casimirs. So if this is done carefully, then we can actually end up with some symplectic submanifold, at least locally, inside M. And then all the structures that you're acquainted with in symplectic geometry can be applied there. One particular important construction, one particular important theory, which is related to symplectic geometry, is which you have probably heard, is the construction of Liouville integrability. Let me recall that if you have a Hamiltonian system defined by Hamiltonian function h, and that is to say its Hamiltonian vector field, you consider its Hamiltonian vector field v sub h, which is equal to the Poisson bracket up to the sign, the Poisson bracket of h and g, right? Then this system is Liouville integrable if there exists, you can find sufficiently large family of functions, h1 equal to h itself, h2, h3, and hn, such that, well, if we work in symplectic world, then n should be equal to 1/2 of the dimension of the manifold, and in the case which we consider on Poisson structure, we should restrict our attention to 1/2 of the symplectic leaf, 1/2 of the dimension of symplectic leaf. Well, generally speaking, we need a sufficiently large family of functions, right? And well, I say this dimension, it means that actually that h1 through hn are functionally independent. Okay. But the most important property is that the Poisson bracket of Hi and Hj vanishes identically. So the problem of finding sufficiently large families of functions that would commute with each other on a manifold, on Poisson manifold, is a pretty renowned and old problem, which dates back to the 19th century, right? Which is actually contemporary to Hamiltonian mechanics, to Liouville theorem. So, well, since it's pretty old, since this problem is pretty old, there have been lots of ideas and constructions used by various authors to obtain large families of commutative functions, large commutative families of functions. Let's put it this way. I'm not going to survey all these methods. There are lots of them. Some of them are pretty interesting. Some of them are pretty special. But I'm going to talk about one particular construction that allows you sometimes to produce a large commutative family of functions on a manifold, beginning with central elements. So suppose we have a manifold M with Poisson structure pi on it. And let us assume that we have one more piece of structure. It is a vector field psi on M, such that, I'm sorry, it seems that it doesn't want to draw for some reason, I don't know. Okay. Such that the following is true. So first of all, we take the derivative of pi in direction of psi. And this need not be equal to 0. It can be equal to 0, but then it means we don't get obtain anything interesting. Let us assume that this is not 0. But the square of the derivative, when you apply it to the same by vector pi, should give you 0. In this case, the following is true. For any two functions, f and g, in the space of Casimir functions, I don't know, let's just write it as Casimirs. Okay, and any two natural numbers, p and q, well, greater or equal to 0. If you take p-fold derivative of f along psi and q-fold derivative of g along psi, then their Poisson bracket of these two functions will vanish identically. So these two functions will Poisson commute. Okay. As you see, the problem with the assumption that the derivative of pi along psi is equal to 0 is that if this is the case, then we don't obtain anything new from this activity. Actually, if this derivative vanishes, then psi of f will always be Casimir if f is Casimir. And so it gives us nothing new, although the same theorem, the same formula hold identically, will hold. But that's nothing interesting. In general case, when psi is of the genuine vector field with this property, not just Poisson vector field. In this general case, these functions f psi p of f and psi q of g will not be central anymore, but they will still commute. And the proof of this fact is so simple and so instructive that I probably give you a few first steps towards this proof. So we begin with the following pretty simple observation, that when you take the identity, take not the identity, take the Lie bracket, the Poisson bracket, so take the Poisson bracket of f and g, and differentiate it along psi, what you get is psi of f commuted with g plus f commuting with psi of g plus the commutator of f and g, but with respect to the derived Poisson bracket. That is to say, here we have the Lie derivative of pi, which is a bivector again, into which we substitute the differentials of f and g. So if we just now change this formula a little bit, we get that the commutator of f and g with respect to the derived Poisson bivector is equal to the following linear combination of expressions: psi f comma g plus f comma psi of g minus psi of the commutator f and g. So this is true for all functions. And let us apply this formula. This is a very simple formula. Let us apply it to the to the equation f g equal to 0 whenever f or g Casimir. So what do we get? So if both f and g are Casimirs, then it gives us the following identity: psi f g plus f psi g minus psi f g equal to 0, equal to commutator of f and g sub psi, right? But on the left, we have identically, all the terms on the left are equal to 0 identically, right? The first one is equal to 0 because g is central. The second one is equal to 0 because f is central. The third is equal to 0 because the argument which we substitute into psi is equal to 0, right? So what we get is the identity at the commutator of f and g sub psi is equal to 0. Now we can do the same trick with the identity psi of f g equal to 0, right? So when we differentiate, we get psi square of f g plus psi f psi g minus psi of psi f g, and it is equal to psi f g sub psi. So the first term here vanishes because g is central. The third term again vanishes because the argument of psi is equal to 0, and we get the identity that psi f psi g is equal to psi f g sub psi. But we can do the same trick with the equation f psi g equal to 0. So this gives us more or less the same expression. And on the right, we have psi f, sorry, not psi f, f psi g. And this is equivalent to psi f psi g is equal to f psi g sub psi. So we finally apply the same trick to this equation, and it will give us psi f g sub psi plus f psi f psi g, sorry, sub psi minus psi applied to f g sub psi is equal to f g sub psi square. So sub psi square is the second Lie derivative of the Poisson bracket. So it finishes identically, right? So whatever we have on the right, we have 0. And on the left, this term is equal to 0 because the argument is gain equal to 0. So what we have on the left is the sum of this term and this term, which is the same as twice the commutative of psi f and psi g. And we conclude that the commutator of psi f and psi g vanishes. And this is actually the case. So this reasoning can be now reproduced by induction for all possible pairs of P and Q, and prove the equation psi P of f comma psi Q of G equal to 0. So this is by induction. So the interesting fact is that here I only used.
May I ask a question?
Yeah.
When you did a proof, you assume that f and g are in the center, but now psi f and psi g are not in the center, I assume, and therefore your induction would not work.
It does, because we actually have not only this, we have only the equation psi f g sub psi equal to 0, and f psi g sub psi equal to 0. So we have 3 equations, and we can add 2 more equations to this psi square f g equal to 0 and f psi square g equal to 0. And at every stage we have analogs of these equations. At every stage, if we use them all, then we are done. So just very careful induction. Not much to do here actually, but it works. I checked it, which is remarkable that actually we don't need very much here. We only need the centrality and also the equation, which was at the previous slide. Here, this equation. that this Lie derivative of the Poisson bracket is equal to this combination of expressions, and the equation that L squared applied to P is equal to 0 means that means that psi f g plus f sub psi g psi is equal to psi f g sub psi. So this equation is sufficient actually. So it works not. It's remarkable that we don't actually need anything. We don't need the assumption that that psi is derivation. We don't need the assumption that pi is Poisson bracket that verifies Jacobi identity. We don't even need actually that to assume that pi is symmetric or skew symmetric, because we can just speak about left and right centers instead of just some elements, just central elements. So it will work perfectly. This reasoning works perfectly well for under any assumptions, and that makes so this simple proof makes the following question the more plausible, the more intriguing question. Is it possible to construct similar algebras in quantizations of the Poisson manifold? What I mean that according to, say, Kontsevich, for instance, theorem, for every Poisson manifold M with Poisson bracket Poisson structure pi, there exists a unique up to equivalence relation star product that takes two functions f and g in M on M and sends them to the following formal series with formal variable h bar, which starts with f times g, the first term being the Poisson bracket of f and g, and the rest is given by certain quite complicated formula. I'm not going to talk about this right now, but this bk of f and g, there are certain differential operators in f and g. So this star product is associative, but not commutative, and this is called the deformation quantization. And the functorial properties of this deformation quantization are quite mysterious. I think they are not sufficiently studied so far. In particular, very little is known about what commutative families can be moved from classical part, from M pi to the deformed pi, and the deformed side to the deformation quantization side. So, instead of speaking about the most general situation, which is pretty complicated, I'm going to speak about very particular case of this. So let us restrict our attention to the situation where M pi is equal to the dual space of a Lie algebra with canonical Lie Poisson structure, which is given by identifying functions, polynomial functions on G star. Well, I just going to use some very informal notation. This equivalent sign doesn't mean that we that every function is polynomial, but we will restrict our attention just to polynomial functions, and they can be identified with just symmetric algebra of G. And the Poisson bracket pi is given by identifying linear functions on G star with elements of the Lie algebra G. So if we have two linear functions x and y, x and y, their Poisson bracket is by definition equal to their Lie bracket. So x capital and y capital are just elements in the Lie algebra which correspond to these linear functions. So that's more or less the standard way of defining the Poisson structure on the dual space. And one can prove, it's not very hard actually, that the deformation quantization in this case, this mysterious star product, can be identified with universal enveloping algebra of G equipped with the standard product in it. Now, when we have a Lie algebra, it is very easy to find a vector field psi on this space G star, dual space of G, that would verify the condition we need with respect to this Poisson bracket. And this is done just by observing that the coefficients of this bivector pi are linear. So linear with respect to the standard affine coordinate system on M. And when you have a linear function, if you want to kill it by some differential, by some vector, by applying into some vector field, you can just take any constant vector field, and square will kill any linear function. So you just take psi to be constant. Constant in the sense that its coefficients are constant when you consider the standard affine coordinates on M. The first, so when you do so, you actually obtain some commutative subalgebra in the in the symmetric algebra of G, Poisson commutative subalgebra. This Poisson commutative subalgebra can be shown to be not just some subalgebra; it is maximal commutative subalgebra, at least when psi is regular. Regular element in, well, I write G because I identify G and G star, for instance, by setting up some killing form between them, non-degenerate, as I assume. There is a definition of regularity in the general case, but for me, if it is sufficient to consider G equal to G semi-simple, in this case, there is natural identification between G and G star. In that case, being regular means that G belongs to a unique Cartan subalgebra. Sorry, psi belongs to a unique Cartan subalgebra in G. So let psi be regular, then this subalgebra generated by the method which I described with respect to psi and the Casimir functions in SG, this subalgebra will be maximal commutative. So this maximal commutative subalgebra is usually called the argument shift algebra. I denote it by S sub psi. Or Mischenko and Fomenko algebra, because their paper was the first paper where this method was explicitly formulated, and where they actually proved that for regular elements you get maximal commutative. Now, this was in 1978, I believe. And of course, they were not the first to observe that this algebra is commutative. I think I am obliged to say that they actually built their construction on the observation originally made by Manakov a couple of years earlier in a very particular case of what they call now Euler-Arnold system on orthogonal group. So it was 1978, end of 70s. And in the beginning of 90s, 1991, this construction was studied by Weinberg. And in addition to giving certain abstract description, abstract characterization of Mischenko and Fomenko subalgebra, Nierga formulated the following question. Is it possible to find a commutative subalgebra, a head sub psi in the universal enveloping algebra, UG, such that when you go from UG to its graded algebra, I'm not going to explain. It's standard thing. If you know the Poincare-Hopf theorem, it can be phrased as follows. When you take the natural filtration of the universal enveloping algebra, of a Lie algebra, take the graded algebra associated with this filtration, and then this graded algebra is naturally isomorphic to the symmetric algebra. So if you take now A hat sub psi and do this procedure, it should go to A sub psi, the Mischenko and Fomenko subalgebra. So that is the question: is it possible to find it? So the answer to this question has been found, at least in the case of classical series of semi-simple Lie algebras by various authors, beginning with 1997, I believe, work by Olshansky and Nazarov. Then in 2001, there was a paper by Weinberg's disciple, I think it was Alexei Tarasov. There is another Tarasov, so I believe it's important to give his name here. And later, 2006, in another construction, yet another construction was given by Leonid Rybnikov. And the final illustrator to this construction was added by Molev and Yakimova and others, who actually gave explicit list of generators of this subalgebras A hat sub psi. For classical series. Of Lie algebras. However, all these constructions, so there are lots of constructions, they are very interesting, they are ingenious, they use different interesting constructions, interesting ideas, like Yangians, which is due to Olshansky and Nazarov, like Katz-Moody algebras, introduced by into the play by Rybnikov, some explicit computations, and so on. However, there is one general feature of all these approaches, which I believe is a little bit, well, let me put it this way, a little bit deplorable, okay? And this is the following. All these constructions begin with considering certain set of generators of the center of the universal enveloping algebra. Actually, not even universal enveloping, but even of the center of a Poisson center of SG. Then you take derivations of these elements. So let it be C1, Cn capital. Take the derivations, and it this gives you a set of generators of the Mischenko and Fomenko subalgebra. And then what these authors did, they all found in one or another way suitable elements in the universal enveloping algebra, which you can describe as psi hat, psi p of ci hat, generic hat, which would commute with each other and which would somehow cover the generators of a psi. And these elements are now announced and are now decreed to be the generators of a hat sub psi. In other words, as you can see, if you just want to take an element f in the center, in the Poisson center of SG, take its derivative, p-fold derivative. And if you want to derive to raise it to something in a hat sub psi, you need to first decompose these, decompose these as the polynomial of generators psi p ci. Then you raise these elements one by one to the universal enveloping algebra, and that will give you an element in a hat sub psi, which is doable, of course, but pretty, well, cumbersome and not very easy. Well, even because when you want to decompose certain element as a, well, in a combination of generators, it is not always weak. Okay. In other words, the most important part of the Mischenko and Fomenko construction, the shift operator, psi from SG to SG, the derivation psi, is missing in universal enveloping algebra. So I'm going to talk now in the remaining part of my talk, which is about 40 minutes. I'm going to talk about the way you can amend this somehow. Namely, I'm going to describe an operator and explain why this operator verifies the conditions we want it to verify. And I'll do this only in the case of G equal to GLN. So let G equal to GLN, the standard Lie algebra of matrices, n by n matrices, then I can describe the operator, which I will denote by psi hat. And this operator will be such that if you take its iterated powers and apply it to any two elements in the center of the universal enveloping algebra, they will still commute. So this operator will definitely cover the partial derivation in the direction of the vector field psi. So that's evident. And I must warn you from the very beginning that if you want to, the naive way to extend this operator from GLN to power to the classical series of semi-simple Lie algebras does not work. Unfortunately, there are counterexamples. What we can prove still that if you take this naive extension of this operator from GLN to any classical series and apply this psi to the generators of the center of the universal enveloping algebra, then you will get still commuting elements. So you can still obtain some generators of the argument of the Mischenko and Fomenko algebra in the universal enveloping algebra. But this property, it holds here for any f and g in the center of the universal enveloping algebra GLN, does not hold, unfortunately. So I'm going to talk about this operator now. So let me recall that GLN is the algebra generated by the elements E, I, J. I prefer to write lower and upper and lower indices here. I, J varies from 1 to n, which verify the commutation relation as of the following form. E, I, J commuting with E, P, Q is equal to delta I, Q, E, J, P minus vice versa, delta J, P, E, I, Q. That's just to set the notation, because actually there are different ways to write down this commutation relation. I'm going to stick to this one. So the universal enveloping algebra, UGLN, can be actually regarded as the algebra with generators EIJ modular this relation EIJ EPQ equal to this. So in order to define the operator psi hat, I'm going to use the partial quasi-derivatives. So there are, well, these operators were first introduced as a separate entities by Gurevich, Pyatov, and Saponov in 2011, I believe. Although, of course, they should have appeared in earlier papers, just because they can be defined in a number of very different ways. You can use quantum double construction of Greenfield. You can use representation of the Lie algebra construction. You can use some geometric constructions and so on and so forth. So there are lots of ways to define them. So I would, giving the credit to Gurevich, Pyatov, and Saponov, I think still it is necessary to warn everyone that, of course, these operators are not very new. They should have been known earlier, but probably people didn't just pay the attention. So what are these quantum quasi-derivations, quantum partial quasi-derivations? So they are operators. So the simplest way to define them is by giving a list of their of axioms that are verified by these operators. So quantum quasi-derivations are operators d hat AB from UGLN to UGLN, verifying the following three axioms. So the first axiom is pretty natural. D hat AB should vanish when applied to the scalars. Of course, in usual case, this is a consequence of the Leibniz rule, but in our case, Leibniz rule will be deformed. So just to be on the safe side, I prefer to introduce this additional condition as well. Next, d hat AB, when you apply it to Eij, should give you delta function. So in this case, I'm using delta functions, the canonical deltas, just preserving the lower and upper indices. So these two equations are natural and very simple, but the most important is the deformed Leibniz rule, which goes as follows. If you take d hat AB and apply it to a product of two functions, f and g, in the universal enveloping algebra, you should get three terms. So the first term is just, the first two terms, I would say, is just the Leibniz rule, usual Leibniz rule, verified by d hat AB. But if it were like this, there wouldn't be a problem at all. Unfortunately, this is impossible because of the commutation relation in universal enveloping algebra doesn't allow this. So we need to add a correction term. In general, there are lots of ways to introduce these correction terms to the Leibniz rule. And the most remarkable thing about the construction of Gurevich, Pyatov, and Saponov is that in this case, we get a very concise and very natural form of this Leibniz rule, because there are Leibniz rules which would involve infinite sums of operators here, but in this case there is just one more term written down as a sum. It is plus sum for k from 1 to n d b k hat f dk a hat of g. So one can check by straightforward computation that these three axioms give a unique set of operators which commute with each other and which verify these three axioms. And now we can define our quantum shift.
May I question at this moment?
Yeah, sure.
So you do have ideal, which you build your universal envelope algebra as a free algebra quotient over ideal, right?
Yeah, sure. Yeah.
Now, these operations DAB hat, if you apply to ideal, do they send this ideal into itself?
Yeah, they will. That's precisely why they're well defined. Yeah.
So that has been checked, right?
Yes. Yes.
Okay.
Yeah. There are a list of ways you can introduce these operations. One can play with these constructions, modify them somehow, and so on and so forth. But so far, in spite of playing with these constructions, I haven't found a better way to introduce it. So if you want, we can discuss this later. So we can finally define the operator psi hat just by saying that suppose we have a matrix psi, numerical matrix, complex or real, doesn't matter. So we just take this metric psi, take the matrix D hat composed of these partial quasi-derivations and take the trace of their product. So in coordinates, it means that we take psi AB, D hat AB, and take the sum over A and B. And now, so this is the operator psi hat, and the main theorem which I was about to talk here, is that this operator actually verifies the condition which I listed, which I mentioned before. So this operator, a theorem, for any two elements F and G in the center of the universal enveloping algebra GLN, for any P and Q non-negative integers, if we take psi P hat applied to F and psi Q hat applied to G, we get 0 as their commutator. So I'm going, in 15 minutes, I'll sketch the main steps of the proof. Because actually the proof is not very interesting. It is very technical. It is, I'm sorry to say, I don't have an explanation of why this happens with the operator psi hat, and why this doesn't happen when you change the Lie algebra from GLN to something more general. I can just prove this by some very, well, I would say something very ad hoc construction based on the following result due to Leonid Rybnikov. So the key result which I am going to use to prove this theorem is due to Leonid Rybnikov, and it is a characterization of the algebra A hat sub psi. The theorem is followed as follows. Oh, sorry. Rybnikov theorem. The algebra A hat sub psi is unique. Well, the algebra A hat sub psi that solves the Windberg's problem. It is unique, and moreover, it is uniquely determined by its quadratic part. So when I say quadratic, since this algebra is not graded, I need to explain. When I say quadratic, it means that I use filtration rather than grading to define quadratic part, linear part, and so on. Namely, when I say quadratic, it means that when I say quadratic, it means that I consider only the elements in the algebra that are generated by elements in the tensor product of degrees no more than 2. Quadratic part. And this part is actually easy to describe. Well, consists of, not is, consists of 1, the expressions. Oh, I forgot to mention one condition. Sorry, what's wrong? Here it is. So we suppose that psi is diagonal matrix with distinct eigenvalues. So we assume that this is the case. Then, under this assumption, this algebra is uniquely determined by its quadratic part, and this quadratic part consists of the polynomials, the quadratic polynomials, just kind of polynomials, quadratic polynomials of I1, E, and N. So take all the diagonal elements in the matrix and take the polynomial in them, and two of elements Ti of psi I equal to 1 through n, where Ti of psi is equal to the sum over j not equal to from 1 to n, j not equal to I. Ej Eji divided by lambda I minus lambda j. So it is remarkable that this theorem has been proved even before the existence of the argument shift algebra, the quantum argument shift algebra A hat sub psi was finally established. So it was proved that if this algebra exists, it should be equal to the centralizer of this set of elements. So let me write this down. So the original paper of Rybnikov said that if A hat sub psi exists, it is centralizer of E1, 1, E and N, and Ti of lambda, of psi. And since it is proved that A hat sub psi exists, we can reformulate this as follows. The centralizer of E1, 1, E N N, T1 psi, T N psi is commutative. You see, because if we have a centralizer, it's automatically in the algebra hat, which is known to exist and which is known to be commutative. So this is true when psi is diagonal. So if psi is diagonal, the proof will consist, proof of the theorem which I mentioned, consists of checking that psi hat P applied to F commutes with EII and commutes with TI of psi for all I and all P. So if psi is not commutative, if psi is not commutative, so what do? We observe that the Lie group GLN acts by conjugation on UGLN, and this action takes psi hat to the operator which you construct by conjugating the operator the matrix psi. But we know that almost any matrix can be, by conjugating, sent into diagonal matrix with distinct eigenvalues. Well, when I say almost any, I mean actually that any matrix except for nowhere dense set. Well, that the space of diagonalizable matrices with simple spectrum is open and dense subset in the space of matrices. Hence, for an open dense subset of matrices, we have psi hat P F commutes with psi Q hat G. And by just continuity of this equation, we conclude that this is true for all matrices. And now a few words about how this is actually proved. And the proof is very naive, I would say, very straightforward, and even, I would say, clumsy in some sense. It is done by induction. You just take the evident equation that F commutes with, say, EII, and apply the operator psi hat to this equation. And then it is easy to see that this is equal to the commutator of psi hat F EII and the commutator of F and some, well, let me see, F tilde and some scalar, which is equal to 0 because scalar commutes with everything. And it means that now by induction we can go from this identity which holds because F is central to the identity psi hat P of F EII equal to 0 for all P and for all II. And then in a similar way we can treat the identity psi P of F commutes with Ti of psi. The base of induction, however, here is a little bit more delicate, because here you need to begin to consider the first derivative of F and show that it commutes with Ti of psi in order to make the induction work. And this is done by explicit description of the image of psi of F on central elements. One can show that the image of psi, when you apply it to the center of UGLN, is a polynomial, kind of polynomial of the following form. You have, it's not a polynomial, it's an expression of the following form. You have certain coefficients alpha k, which are central. And you multiply them by elements of the form trace psi times the matrix of generators of our Lie algebra to the power p. Sum over, not pk, of course. k, of course. Okay. Sum over k, more or less like this. And so since alpha is central, it is sufficient to show that Ti of psi commutes with elements of this form, and this is done by direct computation. It is probably the most complicated computation in the whole proof. And that's more or less how this is proved. So let me again observe that if you try to naively extend these operators from GLN to any other classical Lie algebra, for instance, to the algebra of antisymmetric matrices, by embedding these antisymmetric matrices into the matrices in a natural way by some representation, and then taking the quasi-derivations of the element algebra of GLN of this representation, and restricted to the image of SON, you get some operations, well-defined operations on the universal enveloping algebra of SON, for instance. But these operations will not verify this condition which I mentioned. So that is to say, if you take any two central elements in the universal enveloping algebra of SON and differentiate, take iterated derivatives of these elements with respect to these quasi-derivations induced from GLN, the elements will not commute anymore with each other. That's what distinguishes. So that means that you actually need to do something more than just to naively induce these operations from the large algebra to the smaller algebra. You can somehow do without it if you consider only the generators of the universal enveloping algebra of SON. That's sufficient. In this case, you are still good. This will the elements will commute with each other, but the generic elements will not commute. Even worse than that, if you take the algebra A hat sub psi, let me use red ink here. So if you take A hat sub psi in the universal enveloping algebra of GLN and take the operator G psi hat, which, as I explained, actually does generate in some sense the algebra A hat sub psi, this algebra will not be preserved by the operator psi hat. It actually pushes it outside. So as you see, there are lots of mysteries here. It is not clear at all what other algebras can be somehow extended in this way raised in this way from symmetric algebras to universal enveloping algebras. It is not clear how even to prove this if you don't want to use Rybnikov's characterization of the argument shift of the quantum argument shift algebra with the help of these Rybnikov's elements Ti of psi. So there are lots of questions, lots of mysteries still wide open, and so I hope that some of you will probably take interest in this and probably answer some of these questions. I'll be very happy to know the answer myself. Okay, so since I'm the organizer, I abuse my power to announce that this is the end of my talk, and I invite you to thank the speaker. And I just suggest to ask the questions if you have any. Are there any
Yeah, thank you. Yeah, thank you very much for the talk. So, hello, I have a question.
Who is this? I'm just.
It's Grisha Papayan.
Grigory, very nice to hear you.
Yeah, hello. So this phi that you construct, it's a second order differential operator, right? Am I right?
Sure.
This psi is, yes.
No, it is not second order. It is not. If you consider it as an operator on the symmetric algebra, it's infinite order.
I mean, as an operator on the universal enveloping algebra.
It is hard to define what does it mean being second or
Because
first order differential.
style, when you wrote your modified Leibniz rule,
Yeah, so what?
like it, I mean, well, first order differential operator is that if you compute it with multiplication operator 2 times, it's 0. Second order is that if you compute it with multiplication operator 3 times, it will get 0. It will become 0.
I'm afraid I don't think it is second order. I really don't think so.
Okay, yes.
Yeah, I don't think so. I think it's infinite order. It just
Okay,
if you look at the symmetric algebra, if you consider this operator as operator on symmetric algebra, then this psi will look like the following. You take so psi on symmetric algebra. So I mean, if you take the symmetrization map from symmetric algebra GLN to UGLN, right? And compose it with the operator psi hat, and then take the inverse. So what you get, this combination, sigma minus first, psi hat, and so on, will look like exponential. Well, up to some. Well, you only need to take trace of exponential of the algebra of metrics of partial derivatives.
Okay, yes.
And take the trace. I think it's this.
So I think this symmetrization operator can mess up the order, but yeah.
Yeah, it messes the order, right. It's interesting that as far as I know, this is the only operator which has such small Leibniz rule, if you consider it as the operator on UGLN, because you actually can use more or less similar construction with very well. You can actually extend some operators from SGLN to UGLN using symmetrization and desymmetrization in a similar way, but it is not, as far as I can understand, this is more or less the unique operator which gives you such a concise and simple Leibniz rule. I don't know of any other, but maybe there are, but I haven't seen any other.
Yeah, I mean, I thought maybe you can classify them in some cohomological terms or something. But
yeah, I don't know if there is any cohomological, but they have been somehow described by Miljanac and Skoda some
okay.
years ago. They gave a description of Leibniz rules and so on, but they're pretty complicated. I mean, you always work with infinite sums there. These sums are actually described in terms of certain graphs, certain trees. So there is definitely some relation with Kontsevich quantization there. You can see it, but I haven't seen anybody elaborate in this direction, unfortunately. Yeah.
Okay, thank you again.
Yeah, very welcome. No. So are there any other questions to this speaker?
May I ask you a naive question?
Sure.
So you begin your talk with a proof of the theorem, I mean, of the commutativity using the Poisson structure, right?
Yeah.
And everything works smoothly. I mean, I cannot follow the full details, but I believe you did it everything carefully. Can you apply the lift to the quantum case, like using deformation quantization to move to this result here, the final result? Because what you want to do, you want to move from the Poisson identity to the quantum identity. And is any way to do it using
it's actually the thing which I started, well, I only started to think about this, about 10 years ago. That was actually the original idea. I thought that by some naive abstraction theory, you can raise this, what I would call Nymenher's equation, that the second Lie derivative kills Poisson bracket. You can raise it from the classical world, from Poisson world, to the quantum world. Unfortunately, this equation is not cohomological of its nature. At least I cannot see how it can be made cohomological. It is cubic, not quadratic, unfortunately. It always involves three elements, so to say. I actually tried hard, but I couldn't find a way to squeeze it back into quadratic. And I think this is not just some flaw on my side. It's rather the nature of things, because this equation is closely related to the classical question of bi-Hamiltonian structures, of quantizing bi-Hamiltonian structures. And as far as I know, the deformation theory of bi-Hamiltonian structures is far from being anything developed, anything, well, wide known. Therefore, I was very interested in your talks. Yeah, I realized I am still very, very, curious about how this can be done.
No, the main problem there that if you just apply the Kontsevich argument for bi-Hamiltonian structure, then one Hamiltonian structure give rise to one quantization, one algebra, and another Hamiltonian structure give rise to another algebra, and you cannot put equality in a straightforward way.
That's one of the things how you can put it. Yeah, precisely. There is these things, they are quite robust in being anti-deformation. You see, when you have two Hamiltonian structures, you really need some new ideas. You cannot just do it with the help of some infinity structures or something like that. I heard people try to introduce some special operatic structures to treat this, but I haven't heard about any success in that direction so far. It looks to be quite hard. Yeah.
Thank you.
By the way, I think that let me just abuse my position of a speaker and of the organizer of this seminar and invite you to make a talk here. You can choose more or less any date in November you please. Alexander,
we can discuss it later on.
Yeah, sure. I just officially invite you here. I just bless
Thank
you.
Thank you.
Okay. So any other questions or comments? Okay, so let me thank my audience again for being such a nice audience and asking so much interesting and good questions. And so let us meet next time in a week. Our next speaker will be, I think, Alex Shainman. I'll send his title and abstract next weekend. Thank you again for attending my talk, and see you next time.
Thank you, Gosh.
Thank you.